So let me just adjust this. Right. So we're and move this up here, please. Thank you. So we looked at this illusion here, which you can have another go at as well if you like, because just by pausing it, I'm just going to move this down here for a moment. Oops, let's move it there for a moment. So you just pause it and look at her nose for 20-30 seconds, then look at the thing over there, and that will show you an interesting illusion, which I made a video about a moment ago. If you come over here, then and the previous, in fact, let's go one slide back further. We talked about cones and rods at the back of our eye. I'm looking at slide 6 right now. At the back of our eye, we have these different rods that are more specifically, they're more sensitive to a particular wavelength. So this graph here, which I'll make larger temporarily, you can see that the so-called blue cone is more sensitive to 445 nanometers. The green is more sensitive to 535 by the looks of that. And the red, the so-called red, is more sensitive to 575 nanometers. So when we see a red ball, what's actually happening in our eye is our so-called red cone is detecting a lot more light than the other two, and that with our brain then invents this idea, this concept of red, and so we say this ball is red, and we invent this this idea of what red is, and we see a red ball, and we don't know that the color that I see, that I call red, is the same experience of what you see. We have no idea. Could be the same, could be totally different, but we all agree that this ball is red, that one's blue, and that one's green. And the colours in between, let's say a yellow ball. If I had a yellow ball, well, what would that do? Well, it's going to my so-called green cone was going to detect a fair amount of light, and so will my red cone. And so our brains sort of gets this information that the green cones are detecting light and the red cones are detecting light, and so we invent a new color, and we all collectively call that yellow. So this can be tricked, by the way. Computers do this all the time. In fact, you're being tricked by it right now. When you look at that yellow there, that has got zero yellow light. None of the light is around about 500, let's say 550 nanometers. None of that light is actually 550 nanometers. It's actually a mixture. So that's how we would see yellow light. That we can see yellow light by mixing green and red light. It from our brain's point of view, or maybe you could say our eyes' point of view as well. It's exactly the same experience because the green and the red cones are firing. So if we come back over here, we can look at how these colours can be mixed. So, which I've sort of already mentioned, that we can combine red and green light, and it ends up appearing yellow light, and that happens all the time, and that's what's happening here. And the white light is what we get if we mix all the colors, all 3 colors, or in fact all the colors of the rainbow. You'd get white light. So what would happen if you got some white light and you took away the red light? Well, you'd get the blue and the green, so you'd get this cyan color. And if you took away the green light, you'd get magenta. If you took away the blue light, you'd get yellow. Of course, yellow is a mixture of red and green, or it could be a mixture of yellow, red, and green. So if you took away the yellow light, you'd get blue. If you took away the cyan light, you'd get red, and so on. And this is what a negative color is. So the negative of blue would be, the negative of yellow would be blue. The negative of magenta would be green, and so on. We could also call these ones up here secondary light colors, and these ones, these ones down below are primary light colors. So you can do a little trick here. If you stare at any one of these for 20-30 seconds and then stare at the white square, you will see the negative of that color. For example, you stare at the cyan one for 20-30 seconds and then stare at the white square, you'll see a red square. If you stare at the green one and that for 20-30 seconds, and you'll stare at the white square, you'll see a magenta square, and so on. So this shows you how negative colors work. And that's what is going on here. Rather than there being big squares like this, we're seeing thousands or possibly millions of these little squares, and each one of our tiny photoreceptors at the back of our eye are detecting these. And what's happening is they're getting all tired. So just like when you stare at this this cyan square, the blue and the green cones at the back of our eye and our retina is getting all tired. Meanwhile, the red one, which isn't involved in producing cyan light, that one's getting a rest. And so when you look at the white light, it's only the red ones that have all the energy. And so the white light is a mixture of all the different colors, and it's only the red cones that are able to detect anything or much, because they're the ones that have had the rest. And so stare at this one, and then stare at this, you'll see a red square. Stare at the red one, then stare at this, you'll see a cyan square. And hopefully that explains it. I'll just stop that there.